Something out there is breathing. Not metaphorically, not in some poetic sense that makes for good science fiction or late-night philosophical conversations. We're talking about an object from another star system that appears to be pumping gas into space at perfectly timed intervals, every 16 hours, like clockwork, like a heartbeat. And the thing is, comets don't do that. They shouldn't do that. Yet this one does, and the implications of what that means are challenging everything some of the world's most respected astronomers thought they knew. Let me be very clear about what we're dealing with here. This isn't speculation based on grainy images or wishful thinking from enthusiasts who want to believe we're not alone. This is hard data, observational evidence, mathematical analysis from credible institutions using instruments that cost billions of dollars, like the James Webb Space Telescope. We're watching an interstellar visitor, designated 3I Atlas, exhibit behavior that challenges our understanding of how natural celestial objects operate. And right now, as you're listening to this, that object is getting closer to us. Much closer. The pattern was discovered through careful observation of the object's brightness. Astronomers noticed something peculiar. The light reflecting off 3I Atlas wasn't constant. It was pulsing, brightening and dimming in a precise, repeating cycle. Now, you might think that's normal. Plenty of celestial objects show variations in brightness. Rotating asteroids do it all the time as different surfaces face toward us. But here's what makes this different. The timing is too precise, the pattern too regular, and the mechanism behind it doesn't fit with what we know about how comets behave when they're outgassing and shedding material. Professor Loeb, former chair of Harvard's astronomy department and one of the most published scientists in the field, has been analyzing this object intensely. And in his latest breakdown of the data, he's asking a question that most scientists would rather avoid. He's asking whether those jets of gas we're seeing aren't just rotating into and out of view, but actually turning on and off, pulsing, like something is controlling them, like there's an internal mechanism regulating the release of material with the precision of an engineered system. Stay with me here, because in the next 15 minutes, we're going to walk through exactly what's happening with this object. We're going to look at the observational data that led to this discovery. We're going to examine the mathematics that Loeb used to determine whether this is just rotation or something far more unusual. We're going to explore what it would take, physically, for jets to pulse on and off with this kind of regularity. And we're going to discuss what it means if the answer isn't something natural. We're going to cover the evidence, the analysis, and the implications of a mystery that's unfolding in real time, with a deadline attached. Because on December 19th, 3I Atlas makes its closest approach to Earth, and that's when we might finally get answers. But first, I need to know you're as curious about this as I am, because if you're the kind of person who thinks the universe still has surprises left for us, if you're someone who believes that asking difficult questions is more important than protecting comfortable assumptions, then hit that like button right now. Let me know you're here for the full investigation. Drop a comment and tell me what you think could cause a comet to pulse like a heartbeat. Is there a natural explanation we're missing? Or are we looking at something that challenges everything we thought we knew about interstellar objects? I want to hear your take, because this is the kind of mystery that doesn't come along often, and we're all watching it unfold together. Now, let's talk about what makes this heartbeat pulse so significant. When we say an object is pulsing, we're not talking about a vague sense of activity or some poetic interpretation of data. We're talking about measurable, repeating changes in brightness that correspond to physical processes happening on or within the object. In the case of 3I Atlas, observers have documented a cycle that repeats every 16.16 hours. Not approximately 16 hours, not roughly that time frame, 16.16 hours. That level of precision is what catches attention. That's what makes scientists pause and take a second look. The discovery of this pattern didn't happen overnight. It required multiple observations from different instruments, cross-referencing data, and building what astronomers call a light curve. A light curve is essentially a graph that shows how an object's brightness changes over time. For most comets, you'd expect some variation. As they tumble through space, different surfaces catch sunlight at different angles. As they release gas and dust, the clouds surrounding them can brighten or fade. But those variations are usually irregular, chaotic even. They're the result of complex, unpredictable interactions between the comet's rotation, its composition, and the forces acting on it. What they're not is regular. They're not a repeating pattern you could set a clock to. 3I Atlas is different. The light curve shows a pattern that repeats with remarkable consistency. It brightens, it dims, it brightens again, over and over, every 16 hours. And here's where it gets interesting. The brightening corresponds to periods when we detect increased activity from the jets. These jets are streams of gas and dust being expelled from the comet's surface as it warms up. For most comets, especially ones coming from the cold depths of interstellar space, you'd expect jet activity to be triggered by solar heating. The closer they get to the sun, the more they outgas. But the jets on 3I Atlas aren't behaving that way. They're not gradually increasing as the object approaches the sunday, they're pulsing, turning on, reaching peak activity, then dimming back down, then starting the cycle all over again. This is where Loeb enters the picture, and his involvement matters because of who he is and what he's willing to examine. Loeb isn't a fringe researcher or someone chasing attention through sensational claims. He's published more than 700 papers in peer-reviewed journals. He's received significant recognition in the field of astrophysics. He's led major research initiatives, and he's also someone who's built a reputation for asking questions that make other scientists uncomfortable. He was the lead voice suggesting that Oumuamua, the first confirmed interstellar object we detected back in 2017, might have been something other than a natural asteroid or comet. That suggestion earned him both criticism and respect, depending on who you ask. But what it demonstrated was a willingness to follow the data wherever it leads, even if that means considering possibilities that challenge conventional thinking. When Loeb turned his attention to 3I Atlas, he brought that same approach. He didn't start with an assumption about what the object must be. He started with the observations and asked what they actually tell us. And what they tell us is that something unusual is happening. The pulsing pattern is real, it's documented, it's repeating. The question isn't whether it's happening, the question is why. And that's the mystery we're about to dig into, because the answer has implications that extend far beyond this single object. It touches on how we detect anomalies in space, how we interpret data that doesn't fit our models, and what we're willing to consider when the evidence points in unexpected directions. Right now, 3I Atlas is on a trajectory that brings it closer to Earth than it's been since it entered our solar system. That closest approach happens on December 19th. Multiple observatories are preparing to aim their instruments at it. The James Webb Space Telescope has observation time allocated. Ground-based telescopes are coordinating their efforts. Amateur astronomers around the world are pointing their equipment skyward, hoping to capture whatever data they can. Because everyone involved in this knows that this is a unique opportunity. Interstellar objects don't pass through our neighborhood often. We've only confirmed 3 so far. And of those 3, 3I Atlas is the one exhibiting behavior that doesn't fit the pattern. It's the outlier, the anomaly. And in science, anomalies are where discoveries happen. So here's where we stand. We have an object from another star system. We have documented evidence of a repeating pulse in its brightness and jet activity. We have one of the world's leading astronomers publicly questioning whether that pulse could be something other than simple rotation. We have a deadline approaching when we'll get our best chance to gather more data. And we have a mystery that, depending on how it resolves, could either deepen our understanding of how comets behave or force us to reconsider some fundamental assumptions about what we might encounter when objects from other star systems pass through ours. That's what we're dealing with. That's why this matters. And that's why we need to walk through the evidence carefully, methodically, and with open minds. Let's start with what we're actually seeing when we look at 3I Atlas. When astronomers observe a comet, they're not just taking pretty pictures. Every image, every spectrum, every measurement is data. It's evidence. It tells a story about what that object is made of, how it's moving, what forces are acting on it, and how it's changing over time. With 3I Atlas, that story has taken some unexpected turns, and understanding those turns requires us to look at what the observations actually show, without jumping ahead to interpretation or speculation. Let's look at the raw evidence first. The primary tool for detecting the pulse is photometry. That's the measurement of light intensity over time. When you point a telescope at 3I Atlas and measure how much light is reflecting back toward you, you're capturing a snapshot of its brightness at that specific moment. Do that repeatedly over days and weeks, and you build up a record. That record is the light curve. For 3I Atlas, the light curve shows clear, regular variations. The object brightens significantly, holds that peak brightness for a period, then dims back down. Then it repeats. The entire cycle, from one brightness peak to the next takes just over 16 hours. Now, brightness variations aren't uncommon in comets. As I mentioned earlier, rotation can cause changes in reflected light as different surfaces come into view. A comet with an irregular shape might appear brighter when a large, reflective surface faces you and dimmer when you're looking at a darker region or a narrower profile. But here's the thing. The brightness changes we're seeing with 3i Atlas are more dramatic than what you'd expect from rotation alone. They're not subtle. They're pronounced, and they correlate directly with increased activity in the jets. The jets themselves are visible in imaging data. When 3i Atlas is at peak brightness, telescopes capture distinct plumes of gas and dust extending away from the nucleus. These aren't diffuse clouds, they're directional streams, jets, and they appear to be more active, more intense during the brightness peaks. When the object dims, the jet activity appears to decrease. That correlation is significant. It suggests the brightness changes aren't just about what surface is facing us. They're about actual changes in how much material the comet is expelling. This is where the comparison to normal comet behavior becomes important. Most comets, when they're actively outgassing, maintain a relatively steady level of activity that gradually increases or decreases based on their distance from the sunday. As they approach, solar heating intensifies, sublimation increases, and jet activity ramps up. As they move away, things calm down, but within that overall trend, you don't typically see rapid cycling. You don't see jets that turn on strong, then dial back down, then turn on strong again, all within the span of hours. That's not how sublimation-driven outgassing usually works. Sublimation is a thermal process. It responds to temperature changes. And temperature changes on a comet, especially one the size of 3i Atlas, don't happen that quickly. Think of it this way. Imagine you're heating a pot of water on a stove. As the temperature rises, you start to see steam coming off the surface. If you turn up the heat, you get more steam. If you turn it down, you get less. But you don't see the steam suddenly intensify, then stop, then intensify again in a perfectly timed cycle while the heat source remains constant. That would suggest something else is happening. Maybe there's a lid being placed on and removed from the pot at regular intervals. Maybe there's a mechanism controlling the release of steam independent of the heat source. The point is, you'd be looking at something beyond simple thermal response. That's the situation with 3i Atlas. The sun is the heat source, and its intensity changes gradually as the comet's distance changes. But the jet activity isn't changing gradually. It's cycling. And that cycling doesn't correlate with rapid changes in solar distance because the comet's speed and trajectory don't allow for that kind of variation over a 16-hour period. The object isn't moving far enough in 16 hours to experience a meaningful change in solar heating. So, if the jets are pulsing, something other than changing solar intensity must be driving that pulse. The precision of the cycle is another factor that stands out. 16.16 hours isn't a round number. It's not approximately 16 hours with some variation. It's consistent. That suggests we're observing a fundamental property of the object. Most likely, it's the rotation period. The object spins on its axis, completing one full rotation every 16 hours. That makes sense. Many comets have rotation periods in that general range. But here's the question that Loeb is asking. If it's rotating every 16 hours, why do the jets appear to pulse with that same period? Is it because the jets are fixed in position on the surface, and we're only seeing them when they rotate into view? Or is it because the jets themselves are turning on and off as the object rotates? On the surface, those might seem like two ways of describing the same thing, but physically they're very different. In the first scenario, the jets are continuously active, constantly streaming gas into space, but we only see them when they're pointed in our general direction. It's like a lighthouse. The light is always on, but you only see the beam when it sweeps past you. In the second scenario, the jets are actually shutting off and restarting. The outgassing stops, then begins again. That would require some kind of mechanism, some internal process that regulates the release of gas independent of continuous solar heating. That's a much stranger situation, and it's much harder to explain with standard comet physics. The observational data alone can't definitively distinguish between those two scenarios. If you're looking at an object from a fixed position in space, and you see periodic brightening, you can't immediately tell whether that's because something is rotating into view or because something is actually turning on and off. You need additional information. You need to analyze the geometry of the situation, calculate how far the outgassing material should travel during one rotation, and compare that to what the light curve actually shows. That's where the mathematics comes in. That's where Loeb's analysis becomes critical. But before we get there, it's important to appreciate just how unusual this observational data is. Most comets don't show this kind of regular periodicity in their brightness. Most don't exhibit jet activity that correlates so tightly with brightness variations. Most don't display such precision in their cycles. When you stack up all these observations together, you're looking at an object that's behaving differently than the majority of comets we've studied. That doesn't automatically mean it's not a comet. It doesn't automatically mean it's artificial. What it means is that it's an outlier. It's behaving in ways that push the boundaries of what we consider normal. And outliers demand closer examination because they often reveal something new about the processes at work. There's another aspect of the observations worth noting. The jets aren't uniformly distributed around the object. Imaging data suggests they're coming from specific locations on the surface. That's actually common with comets. Outgassing doesn't happen uniformly. It tends to occur in regions where volatile materials are closer to the surface or where the surface structure allows for easier release of gas. Those regions become active areas, and as the comet rotates, those active areas rotate with it. So if we're seeing brightness peaks every 16 hours, it makes sense that we're seeing active regions come into view, reach maximum visibility, then rotate out of view. That's the rotation hypothesis. That's the straightforward explanation. But the intensity of the peaks, the sharpness of the brightness changes, and the apparent on-off nature of the jet activity are what make this more complicated. Because if the jets were just rotating in and out of view, you'd expect a more gradual brightness curve. You'd expect to see the brightness slowly increase as the jet rotates toward you, peak when it's directly in view, then slowly decrease as it rotates away. A smooth rise and fall. What the light curve shows is sharper than that. The brightness changes more abruptly. That's more consistent with jets that intensify quickly, maintain peak activity, then drop off quickly. And that behavior is harder to explain with rotation alone. So we have a puzzle. The observations show clear periodic behavior tied to what's almost certainly the object's rotation period. But the characteristics of that periodic behavior don't quite match what we'd expect from simple rotation of continuously active jets. There's a mismatch between the model and the data. And when that happens in science, you have two options. Either refine the model to account for the data, or consider whether you're missing something fundamental about what's actually happening. Loeb is doing both. He's asking whether the standard model of comet behavior applies to this object, and he's exploring what it would mean if it doesn't. This brings us to the heart of the investigation. The observations have given us the what, now we need the why. We need to understand the mechanisms that could produce this heartbeat pulse. We need to look at the physics, run the numbers, and see what they tell us about which explanation fits the evidence. Because the difference between jets rotating into view and jets actually pulsing isn't just semantic, it's fundamental. And it determines whether we're looking at a comet behaving strangely within the bounds of natural processes or something that requires a different kind of explanation entirely. Let's examine what Avi Loeb discovered when he did the math. Here's where the investigation shifts from observation to interpretation. We've seen what 3i Atlas is doing. Now we need to figure out why it's doing it. And the first step in that process is making sure we're asking the right question. Avi Loeb, in his analysis, frames it very clearly. He's not asking whether the object is showing periodic behavior. The data already confirms that. He's asking whether that periodic behavior is the result of rotation bringing jets in and out of view, or whether the jets themselves are pulsing on and off as the object rotates. It sounds like a subtle distinction, but the implications are enormous. Let's think about what each scenario requires. In the rotation scenario, the comet has one or more active regions on its surface that are continuously outgassing. These jets are always on, constantly streaming material into space. The comet rotates every 16 hours, and as it does, these jets rotate with it. When a jet is pointed generally toward Earth, we see it. The comet appears brighter. When that jet rotates to face away from us, we don't see it. The comet appears dimmer. The brightness cycle we're observing is just an artifact of our viewing angle. It's not that the jets are changing, it's that our perspective is changing. This is the simpler explanation. It doesn't require any unusual mechanisms. It fits with what we know about how comets work. Active regions outgas when they're heated by the sun, and that outgassing can be sustained as long as there's volatile material near the surface and sufficient solar energy to drive sublimation. The rotation brings different regions into sunlight and into our line of sight, creating the periodic pattern we observe. It's elegant, it's straightforward, and for most comets exhibiting periodic brightness variations, this is exactly what's happening. But here's the catch. If this is what's happening with 3I Atlas, then we should be able to predict what the light curve should look like based on the geometry of the situation. We know the rotation period. We can estimate the speed at which gas is being expelled from the jets. We can calculate how far that gas travels during one rotation. And we can model what the brightness pattern should look like as a continuously active jet rotates in and out of our view. When Loeb did those calculations, he found something interesting. The predicted pattern didn't quite match the observed pattern. The observed changes in brightness were sharper, more distinct, than what you'd expect from simple rotation of a continuously active jet. That mismatch is what led him to consider the alternative. What if the jets aren't continuously active? What if they're actually turning on and off? What if something about the object's internal dynamics, its structure, or its composition, causes the outgassing to start and stop in sync with its rotation? This is the pulsing hypothesis. And it's a much stranger proposition because it requires a mechanism. Something has to be regulating the jets. Something has to be causing them to activate during specific phases of the rotation and shut down during others. Now, you might be thinking, why would that be strange? Couldn't there be a natural process that does exactly that? And the answer is yes, there could be. But it's not easy to explain with standard comet physics. Outgassing is driven by solar heating. When ice or other volatile materials near the surface absorb heat, they sublimate directly from solid to gas, and that gas escapes into space, carrying dust with it. This process doesn't turn on and off rapidly unless something is physically blocking the sublimating material from escaping, or unless the heat source is being interrupted. On a rotating comet, different regions rotate into and out of sunlight, but that transition happens gradually. You'd expect a gradual increase in activity as a region enters sunlight, and a gradual decrease as it rotates into shadow. What you wouldn't expect is a sharp on-off cycle, unless there's something else going on, unless the object has some kind of internal structure that regulates the release of gas. Imagine a comet with subsurface pockets of volatile material that periodically breach the surface as internal pressure builds, then seal off again once the pressure is released. Or imagine an object with surface features, maybe cliffs or overhangs, that shade certain regions during part of the rotation and then expose them suddenly as the geometry changes. There are creative ways you could try to build a natural mechanism for pulsing jets, but all of them require special conditions. They require the object to have a very specific structure or composition that most comets don't have. This is where Loeb's approach becomes important. He's not saying the pulsing hypothesis is definitely correct. He's saying it deserves consideration because the rotation hypothesis doesn't fully account for the observations. He's doing what scientists are supposed to do. He's following the data and asking whether our existing models are sufficient or whether we need to expand them. And he's being transparent about the fact that if the jets really are pulsing, we need an explanation for what's causing that pulse. The implications of the pulsing hypothesis extend beyond just understanding this one comet. If confirmed, it would tell us something new about the potential diversity of interstellar objects. It would suggest that objects from other star systems can have internal dynamics or structures that we haven't encountered in objects that formed in our own solar system. That's not a radical idea. Different stellar environments could produce objects with different properties. A comet that formed around a star with a different composition, different radiation environment, or different protoplanetary disk dynamics might have characteristics we don't see in local comets. The pulsing behavior could be a signature of that foreign origin. But here's where things get more provocative. If the pulsing is happening, and if it's happening with the precision and regularity that the observations suggest, then you start to wonder what kind of mechanism could maintain that level of control. Natural processes can be periodic. Orbits are periodic. Rotations are periodic. Tidal forces can create periodic stresses, but those periodicities tend to be larger scale and gradual. A mechanism that turns jets on and off with the precision of a clock, maintaining that rhythm over extended periods, starts to sound more like something that's regulated, something that has feedback loops, something that might resemble what we'd call control. Now, I want to be very careful here, because this is where the conversation can veer into territory that makes people uncomfortable. When you start talking about control mechanisms on an interstellar object, you're edging toward questions about intentionality. You're opening the door to speculation about whether the object could be something other than a natural comet. And that's a conversation that most scientists prefer to avoid because it invites all kinds of unfounded speculation and attention from people who are more interested in science fiction than science fact. But avoiding the conversation doesn't make the data go away. It doesn't resolve the mismatch between what we observe and what our models predict. Loeb's position is that we should be willing to ask these questions, not because we're looking for alien technology under every rock, but because refusing to ask them when the data warrants it is a failure of intellectual honesty. Science advances by questioning assumptions, exploring alternative explanations, and testing hypotheses, even when they challenge the mainstream view. If there's a natural explanation for the pulsing, we need to find it and demonstrate it. If there isn't, we need to be willing to consider what that means. The heartbeat question, then, isn't just about whether jets are turning on and off. It's about whether we're prepared to follow the evidence wherever it leads, even if that path takes us to conclusions that feel uncomfortable or unlikely. It's about maintaining the discipline to separate what we observe from what we assume, and to test those assumptions rigorously before accepting them as truth. That's the scientific method. That's what Loeb is advocating for. And that's what makes this investigation so compelling, because the answer to the heartbeat question will either deepen our understanding of natural cometary processes or force us to expand our framework for what we might encounter when we study objects from beyond our solar system. So let's do exactly what Loeb did. Let's look at the numbers. Let's run through the calculations and see what they tell us about which hypothesis better fits the data, because that's where speculation ends and evidence begins. Mathematics is the language of the universe. It's how we translate observations into understanding. When Loeb analyzed the 3I Atlas data, he wasn't relying on intuition or guesswork. He was applying physics and geometry to determine what the light curve patterns actually tell us about the object's behavior. And what those calculations revealed is both fascinating and perplexing. Let's walk through the logic step by step, because this is where the mystery either gets solved or deepens. The starting point is the outflow velocity. That's the speed at which gas and dust are being expelled from the comet's surface. Based on spectroscopic observations and models of cometary outgassing, researchers estimated that material is leaving 3I Atlas at several hundred meters per second. That's typical for active comets. The gas sublimates, expands rapidly, and carries dust particles along with it, creating the jets and the surrounding coma. So we have a baseline. Gas leaves the surface at a certain speed. Next, we need to consider the rotation period. We know the object completes one rotation every 16 hours. That's derived directly from the periodicity in the light curve. So during one complete rotation, the comet spins all the way around on its axis. If there are jets on the surface, those jets rotate with the object. They start facing one direction, and 16 hours later, they're back to facing that same direction after a full rotation. Now here's the critical calculation. If gas is leaving the surface at several hundred meters per second, how far does that gas travel during one rotation? This is basic physics. Distance equals velocity multiplied by time. The velocity is the outflow speed, the time is the rotation period. When you multiply them together, you get the distance that the gas travels away from the nucleus during one full rotation, and that distance turns out to be tens of thousands of kilometers. Let me put that in perspective. The nucleus of 3I Atlas itself is only a few kilometers across, but the gas cloud being expelled from it, over the course of one rotation, extends tens of thousands of kilometers outward. That's a huge envelope of material. And here's why that matters. If the jets were continuously active, constantly streaming gas into space, then during one rotation, you'd build up a continuous trail of gas, extending all the way around the object. As the jet rotates, it's laying down material along its path. By the time it completes one full rotation, there should be a relatively uniform shell or spiral of gas surrounding the nucleus. When you have that kind of distribution of material, it affects what the light curve looks like. As the comet rotates, you're not just seeing the jet itself, you're seeing the gas and dust that the jet has already expelled, which is now spread out in space. The brightness doesn't drop to zero when the jet rotates away from your line of sight, because the material the jet expelled earlier is still there, still scattering sunlight, still contributing to the brightness. The result is a light curve that shows variation, but relatively gradual variation. You get a brightness peak when the jet is pointed toward you and the material is densest along your line of sight, and you get a lower brightness when the jet is pointed away and you're seeing the more diffuse material. But the transition between those states is smooth. What Loeb found is that the observed light curve doesn't match that pattern. The brightness changes are sharper, the peaks are more distinct, and the dips are more pronounced. It's as if the material isn't forming a continuous envelope around the nucleus. It's as if the jets are active for part of the rotation, creating dense plumes, and then inactive for part of the rotation, creating gaps where there's little or no fresh material being expelled. When you look at the object during the active phase, you see a bright plume. When you look during the inactive phase, you see much less, because there's no fresh material being added and the previously expelled material has had time to disperse. This pattern is more consistent with pulsing. If the jets turn on for a portion of the rotation cycle and then turn off, you'd expect to see exactly what the observations show. During the active phase, a dense, bright plume forms. During the inactive phase, the outgassing stops and the brightness drops significantly because you're only seeing residual material that's already moving away and spreading out. The rotation brings the active region back around, the jets turn on again, and the cycle repeats. The mathematics of this scenario match the observed light curve much better than the continuous outgassing scenario. But here's where it gets even more interesting. If the jets really are turning on and off, what does that tell us about the object's internal structure and dynamics? To answer that, we need to think about what causes outgassing in the first place and what could cause it to stop. Outgassing happens when volatile materials sublimate due to solar heating. For the outgassing to stop, either the heating has to stop, or the material has to be blocked from escaping, or the supply of volatile material has to be exhausted. The heating isn't stopping. The sun is still there, still delivering energy to the surface. Over the course of a 16-hour rotation, the illumination angle changes, but not dramatically enough to account for jets completely shutting off and restarting. So if heating isn't the variable, what is? The most plausible natural explanation is that something is periodically covering and uncovering the active regions. Maybe the comet has an irregular shape with overhangs or craters that cast shadows on certain regions during part of the rotation. When a region is in shadow, it cools down, sublimation slows or stops, and the jet becomes inactive. When that region rotates back into sunlight, it heats up again, sublimation resumes, and the jet reactivates. That's a possible mechanism. It doesn't require anything exotic. It just requires the comet to have the right geometry. But there's a problem. For this to work, the shading has to be very effective. It has to cool the active region down enough to shut off sublimation almost completely, and it has to do so rapidly. And then, when the region rotates back into sunlight, it has to heat up again just as rapidly to restart the jet. That's a lot to ask. Cometary surfaces have thermal inertia. They don't heat and cool instantly. The regolith and subsurface layers retain heat, which means that even when a region rotates into shadow, it doesn't immediately stop outgassing. There's a lag, and that lag should smooth out the brightness curve, making the transitions more gradual. Yet the observations show sharp transitions. That suggests either the shading mechanism is extremely effective, or there's another factor at play. One possibility is that the active regions aren't on the surface in the way we typically imagine. Maybe the volatile material is stored in subsurface reservoirs that periodically connect to the surface through vents or fractures. As the comet rotates, stress from rotation or thermal expansion could open and close those vents. When a vent opens, gas escapes, creating a jet. When it closes, the outgassing stops. The rotation period would determine the cycle of opening and closing, creating the observed pulse. This is more speculative, but it's grounded in known physics. Comets can have complex internal structures. They can have layers of different materials, voids, fractures. Internal pressures can build and release. It's not unreasonable to imagine that such a structure could create periodic venting that's synchronized with rotation, but it does require the object to have a very specific architecture. It's not something you'd expect to see in every comet. It's a special case. And the fact that 3I Atlas is an interstellar visitor makes it even more intriguing, because it suggests that objects from other star systems might commonly have structures or behaviors that are rare in our own solar system's comets. Loeb's mathematical analysis doesn't prove definitively that the jets are pulsing rather than just rotating into view. What it does is show that the pulsing hypothesis fits the observed data better than the simple rotation hypothesis. It demonstrates that the light curve characteristics, when combined with reasonable assumptions about outflow velocity and gas distribution, they are more consistent with jets that turn on and off than with jets that are continuously active. That's a significant finding. It shifts the burden of explanation. Now, the question isn't why we should consider pulsing. The question is why we shouldn't, given that the math supports it. And that brings us to the next level of the investigation. If the jets are pulsing, we need to understand what that implies about the object. Is this still within the realm of natural cometary behavior, just something rare and unusual, or does it suggest something more? To answer that, we need to look at what pulsing jets would require in terms of control and regulation. We need to explore whether natural mechanisms are sufficient or whether we're missing something fundamental, because the mathematics have given us a pattern. Now, we need to understand the mechanism, and that's where the implications start to become profound, because the precision and regularity of this heartbeat pulse aren't easy to explain with the processes we typically invoke for comets. Let's examine what this could mean. When you strip away all the technical jargon and complex calculations, what we're left with is a simple but profound question. If the jets on 3i Atlas are genuinely pulsing on and off with the precision of a metronome, what does that tell us about the nature of this object? Is it simply a comet with an unusual structure that happens to produce this effect through natural processes? Or are we looking at something that challenges our understanding of what interstellar objects can be? This is where the scientific investigation transitions into implications, and where we have to be both rigorous in our reasoning and honest about what the data might suggest. Let's start with natural explanations, because that's always where science should begin. We should exhaust all conventional possibilities before entertaining exotic ones. So what natural mechanisms could cause a comet to pulse its jets with such regularity? We've already touched on a few possibilities. Shading effects from surface topography. Subsurface reservoirs with vents that open and close due to rotational stress or thermal cycling. Compositional variations that create regions with different sublimation rates. Internal pressure dynamics that cause periodic releases of gas. All of these are rooted in known physics. None of them require us to invoke new principles or unknown phenomena. But here's the challenge. Each of these mechanisms requires very specific conditions to produce the kind of sharp, regular pulsing we're observing. It's not enough for the comet to have an irregular shape. The geometry has to be just right, so that shading occurs at exactly the right phases of rotation to create the observed pattern. It's not enough to have subsurface reservoirs. Those reservoirs have to be connected to the surface in a way that allows for rapid opening and closing, and that cycling has to be synchronized with rotation in a way that maintains precision over many cycles. It's not enough to have compositional variations. Those variations have to be distributed in a pattern that produces the observed periodicity. What I'm getting at is that while each individual mechanism is plausible in isolation, the odds of any single one of them naturally producing the precise, sustained, pulsing pattern we're seeing are relatively low, and the odds of them all working together in perfect coordination are even lower. This doesn't mean it's impossible. Low probability events happen all the time in a universe as vast as ours, but it does mean we should be cautious about assuming we've explained the phenomenon just because we can imagine a mechanism. We need evidence that the mechanism is actually operating, and right now, we don't have that evidence. We have a pattern that needs explaining, and a list of possible explanations, none of which have been confirmed. This is where the conversation becomes more interesting, and, for some, more uncomfortable. If standard natural mechanisms struggle to fully account for the observations, what alternatives should we consider? Loeb has been very deliberate in how he approaches this question. He doesn't jump straight to claiming the object is artificial. What he does is point out that when you encounter something exhibiting highly regular, controlled behavior, one category of explanation that naturally comes to mind is that the behavior is intentional, that it's the result of a system designed to produce that specific output. Now, before anyone jumps to conclusions, let's be clear about what that means and what it doesn't mean. Saying something might be designed doesn't require invoking alien intelligence or interstellar probes. Even natural objects can have internal systems that function in regulated ways. Think of pulsar stars. They emit beams of radiation with extraordinary precision, and that precision is the result of their physical structure and rotation. Nobody thinks pulsars are artificial, but they do exhibit controlled, regular behavior because the natural processes governing them are tightly constrained by physics. So, the presence of regular, controlled behavior doesn't automatically imply artificiality, but it does suggest that the object has some kind of internal structure or process that's imposing order on what would otherwise be chaotic. The question becomes, what kind of structure or process? If 3I Atlas has an internal mechanism that regulates jet activity with the precision we're observing, what would that mechanism look like? If it's natural, it would have to be something that emerged through the object's formation and evolution. Perhaps it formed in an environment where tidal forces or radiation pressure created layered structures with periodic weaknesses. Perhaps it underwent collisions or near misses that fractured its interior in ways that created pressure relief patterns. Perhaps it has a composition that naturally segregates into regions with different thermal and mechanical properties, and those regions interact to produce the pulsing effect. All of those are theoretically possible. But here's what bothers researchers like Loeb: the precision. Natural processes tend to produce variation. Even highly regular natural phenomena have some drift, some noise, some irregularity. Orbits aren't perfect ellipses because of gravitational perturbations. Planetary rotations slow down or speed up slightly over time due to tidal interactions. Pulsars gradually spin down as they lose energy. Nature is regular, but it's rarely perfectly regular. Yet the pulsing pattern of 3I Atlas, as far as current observations can determine, is remarkably consistent. That level of consistency is unusual. It's not impossible, but it's unusual enough to warrant close attention. This is where Loeb's work on Oumuamua becomes relevant context. Oumuamua, the first confirmed interstellar object detected passing through our solar system, exhibited anomalous acceleration that couldn't be fully explained by standard cometary outgassing. Loeb suggested that one possible explanation was that the object had a large surface area relative to its mass, like a sail, which could be pushed by solar radiation pressure. He further suggested that if it was a sail, it might not be natural. It might be a probe or artifact from another civilization. That suggestion generated significant controversy. Many astronomers pushed back, arguing that exotic explanations should be the last resort, not the first consideration. But Loeb's point wasn't that Oumuamua definitely was artificial. His point was that we should be willing to consider all explanations consistent with the data, including ones that challenge our assumptions about what exists in the universe. And that approach applies here. With 3I Atlas, we're not starting with the assumption that it's artificial. We're starting with observations that don't perfectly match our models of natural comet behavior. We're noting that those observations suggest a level of regularity and control that's atypical. And we're asking what could produce that. If natural mechanisms can fully account for it, great. We'll have learned something new about comet physics. If they can't, then we need to expand our thinking. One way to think about this is in terms of hypotheses that make testable predictions. The natural pulsing hypothesis predicts that as we gather more data, we'll identify specific features of the object, its composition, structure, or environment that explain the mechanism. We'll find the shading geometry, or the subsurface architecture, or the compositional pattern that produces the pulse. The observations scheduled for December 19th should help with that. High-resolution imaging, spectroscopy, and detailed monitoring of the jets during the close approach will give us much more information. If the natural mechanisms are correct, that data should reveal them. But what if we don't find those features? What if the close approach observations show a relatively uniform object without obvious structural peculiarities that would explain the pulsing? What if the spectroscopy shows a composition consistent with typical comets, without unusual volatiles or stratification? What if the jets continue to pulse with precision, but we can't identify the physical mechanism driving that pulse? At that point, the natural explanation becomes much harder to sustain. And at that point, we're obligated to consider other possibilities, even if those possibilities make us uncomfortable. This is the scientific method in action. You formulate hypotheses, you test them, you gather data, you compare predictions to observations, and you follow the evidence. If the evidence supports a natural explanation, you accept it. If it doesn't, you revise your hypothesis. And if none of the natural hypotheses fit the data, you consider whether you're asking the wrong question or whether you need to expand the set of possible answers. That's not speculation, that's rigor. The implications of the pulsing jets extend beyond just this one object. If 3i Atlas turns out to have a natural but highly unusual mechanism producing this effect, that tells us something important about the diversity of objects in the galaxy. It tells us that interstellar space can forge objects with properties we haven't seen in our local neighborhood. It tells us that when we study future interstellar visitors, we should expect the unexpected. And it tells us that our models of comet behavior, which are based almost entirely on objects from our own solar system, might not capture the full range of possibilities. On the other hand, if the pulsing can't be explained naturally, if it really does suggest some form of internal control or design, then we're facing a much more profound implication. We're facing the possibility that objects traveling between star systems might include things other than natural asteroids and comets. That's a conversation that science has largely avoided, not because the evidence definitively rules it out, but because it's easier to assume it's not happening and focus on more mundane questions. But easier isn't the same as correct. And if the universe contains surprises, we're only going to find them if we're willing to look. What's clear is that 3i Atlas is forcing us to ask these questions. The heartbeat pulse is real. The regularity is documented. The challenge to our models is undeniable. And the December 19th observations represent a critical opportunity to gather the data needed to resolve this mystery. Whether the answer ends up being a fascinating natural mechanism or something more extraordinary, we're in the process of learning something new, and that's what makes this so compelling. This isn't settled science. This is science happening in real time, with real stakes, and real uncertainty about where the evidence will lead. Let's look at the broader context to see if there are other clues that might inform this investigation. The heartbeat pulse isn't the only unusual aspect of 3i Atlas that's captured attention. While it's the most rigorously analysed and the focus of Loeb's recent work, it exists within a broader constellation of reported anomalies. Some of these are well documented and scientifically verified. Others are more speculative, circulating in research communities and online discussions, but not yet confirmed through peer-reviewed analysis. To understand the full picture of what we're dealing with, we need to acknowledge this broader context, while being careful to distinguish between what's established fact and what remains uncertain or contested. One of the more intriguing verified observations is the anti-tail phenomenon. Comets typically develop tails that point away from the sun, driven by solar wind and radiation pressure pushing gas and dust outward. It's basic physics. Light and charged particles from the sun exert pressure on the material released by the comet, and that pressure creates a tail extending in the anti-sunward direction. What's unusual about 3i Atlas is that observers have reported seeing features that appear to extend toward the sun, not away from it. This is called an anti-tail, and while it's not unheard of in cometary science, it's rare and typically associated with specific geometric configurations. An anti-tail can occur when the geometry of the comet's orbit and our viewing angle creates an optical illusion where dust already released from the comet appears to point sunward. It's a projection effect. The dust is actually in an orbital path, but from our perspective, it looks like it's aimed at the sunday. However, for this illusion to be convincing and persistent, the conditions have to be fairly specific. And some researchers have noted that the anti-tail features observed with 3i Atlas seem more pronounced or more persistent than what you'd typically expect from a simple geometric effect. That doesn't mean something impossible is happening. It means the geometry, the dust distribution, or both are unusual enough to produce a striking visual result. Why does this matter in the context of the heartbeat pulse investigation? Because it suggests that the object's behavior is multifaceted. It's not just the pulsing jets. It's the overall pattern of activity and appearance that deviates from the norm. When you have multiple anomalies, even if each one can potentially be explained individually, the cumulative effect is more significant. It raises the question of whether these anomalies are independent oddities or whether they're related symptoms of something fundamental about how this object is structured or how it's behaving. Another area of discussion, though less firmly established, involves the object's trajectory. Some analyses have suggested that 3i Atlas is following a path that brings it unusually close to Earth relative to what you'd expect from a randomly oriented interstellar trajectory. Now, this is where we have to be very careful, because trajectory analysis can be misleading if not done rigorously. Interstellar objects enter the solar system from random directions, and by chance, some of them will pass relatively close to Earth, simply due to the geometry of their paths and the timing of their arrival. Close approaches aren't inherently anomalous. However, What has raised eyebrows in some quarters is the suggestion that the trajectory seems optimized for observation. The object arrived at a time and on a path that allows for extended viewing from Earth-based and space-based telescopes. Its closest approach coincides with a period when major observatories have the ability to focus significant resources on it. Is that just luck, or is it a suspiciously convenient coincidence? The mainstream scientific view is that it's luck. The universe is large, and over time, we'll encounter interstellar objects with all sorts of trajectories. Some will be easy to observe, others won't. The fact that this one happens to be well positioned for study is fortunate, but not necessarily meaningful. But Loeb and others who are more open to unconventional possibilities point out that if you were designing a probe intended to be noticed by a technological civilization, you'd probably aim it in a way that maximizes the chances of detection. You'd want it to pass close enough to be easily observed, during a time when observation is possible. That doesn't mean 3i Atlas is a probe. It means that if it were, its trajectory would be consistent with that hypothesis. It's a matter of considering what predictions different hypotheses make and whether the observations align with those predictions. The trajectory is consistent with both random chance and intentional aim, so by itself, it doesn't prove anything. But it's part of the pattern. Then there are the more speculative claims. Some sources have reported possible radio emissions or electromagnetic anomalies associated with 3i Atlas. These reports are much less substantiated. Radio observations of comets are not uncommon, but they typically detect emissions associated with the interaction of the solar wind with the cometary plasma environment. Any radio signals would need to be analyzed carefully to determine whether they're natural emissions from the object's coma or something more unusual. As of now, there's no peer-reviewed confirmation of anomalous radio signals. That doesn't mean such signals don't exist. It means that if they do, they haven't been verified through the rigorous process that science requires before accepting a claim as fact. Why mention these speculative claims at all? Because they're part of the conversation happening around this object, and ignoring them doesn't make them go away. It's better to acknowledge them, put them in context, and be clear about what's verified and what isn't. The heartbeat pulse is verified. The antitail is verified, though its interpretation may vary. The trajectory is a matter of public record, though its significance is debated. Radio signals are speculative and unconfirmed. When you're evaluating the overall picture, you have to weigh the evidence appropriately. Confirmed anomalies carry more weight. Speculative ones are worth monitoring but shouldn't drive conclusions. What the broader context does is reinforce the idea that 3i Atlas is not a typical comet. Even if every single anomaly turns out to have a natural explanation, the fact that this object exhibits multiple unusual features sets it apart. It's an outlier, and outliers are important in science because they often point to gaps in our understanding. They're the data points that don't fit neatly into existing models, and they force us to refine those models or develop new ones. Comparing 3i Atlas to other interstellar visitors is instructive. Oumuamua was notable for its elongated shape, its lack of obvious cometary activity, and its anomalous acceleration. 2i, Borisov, the second confirmed interstellar object, was much more typical. It looked like a comet, behaved like a comet, and fit comfortably within existing models. It was interesting because it was from another star system, but it didn't challenge our understanding of how comets work. 3i Atlas falls somewhere in between. It's clearly active, clearly exhibiting comet-like features, but those features are behaving in ways that don't perfectly match what we expect. The question is whether these differences are just natural variation, or whether they're telling us something deeper. In any population, whether it's people, planets, or comets, you expect diversity. Not every member of the population will behave identically. Some will be at the extremes of the distribution, so finding an interstellar comet that's a bit unusual isn't shocking. But when the unusual features cluster together, when you have not just one oddity but several, that's when scientists start to pay closer attention. That's when the possibility that you're looking at something fundamentally different becomes harder to dismiss. This is the context in which the December 19th observations will occur. Scientists aren't just looking at the pulsing jets in isolation, they're looking at the whole object. They're trying to understand its structure, composition, activity patterns, and how all of those relate to each other. They're trying to build a comprehensive model that accounts for everything we're seeing. If that model turns out to be a natural comet with some unusual but explicable properties, that's a valuable outcome. If it turns out that no single natural model can account for all the observations, that's an even more valuable outcome, because it means we've discovered something genuinely new. The broader context also highlights the importance of maintaining scientific rigor while staying open to unexpected discoveries. It's easy to fall into one of two traps. The first trap is dismissing all anomalies as measurement errors or misinterpretations, refusing to seriously consider that something unusual might be happening. That's the trap of excessive skepticism. The second trap is jumping to extraordinary conclusions based on limited or speculative evidence, letting excitement override caution. That's the trap of excessive credulity. The path between those traps is narrow, but it's where good science happens. It requires taking anomalies seriously, investigating them thoroughly, demanding high-quality evidence, and following that evidence wherever it leads. That's what the scientific community is trying to do with 3i Atlas. And that's what makes the December 19th close approach so significant. It's not just another observation opportunity. It's a chance to gather the data needed to move from speculation to conclusion, from mystery to understanding. Let's talk about what happens next. December 19th is circled on calendars across the astronomical community. It's the date when 3i Atlas makes its closest approach to Earth, and it represents the single best opportunity. We'll have to study this object in detail before it continues its journey out of the solar system and back into interstellar space. After that, it will become fainter, harder to observe, and eventually disappear from our instrument's view. This is our moment, and researchers are preparing to make the most of it. The closest approach doesn't mean the object will be dramatically close in human terms. We're not talking about something visible to the naked eye, or passing near enough to pose any threat. We're talking about a distance that, while vast by everyday standards, is close enough to allow for much more detailed observations than have been possible so far. Telescopes that have been tracking the object from a distance will now be able to resolve finer details. Instruments that struggled to pick up faint signals will now have stronger data to work with. The close approach is like moving from watching something through a foggy window to stepping outside for a clear view. Multiple observatories are coordinating their efforts. Ground-based telescopes from around the world are scheduling observation windows. These telescopes will capture images in various wavelengths, from visible light to infrared. They'll measure the brightness variations with higher temporal resolution, allowing for more precise characterization of the pulsing pattern. They'll perform spectroscopy to analyze the composition of the gas being expelled by the jets. Different elements and molecules emit light at specific wavelengths, so by spreading the light into a spectrum and looking at which wavelengths are present or absent, scientists can determine what the comet is made of and what processes are driving the outgassing. But the most anticipated observations are coming from space-based platforms, particularly the James Webb Space Telescope. Webb, with its extraordinary sensitivity and ability to observe in the infrared, is uniquely suited to study comets. Infrared observations are crucial because they allow us to see heat signatures and to detect molecules that don't emit strongly in visible light. Webb can map the temperature distribution across the nucleus and the surrounding coma. It can identify specific compounds in the jets, and it can do all of this with a level of detail that ground-based telescopes simply can't match due to atmospheric interference. What are scientists hoping to find? First and foremost, they want to confirm the pulsing pattern and characterize it more precisely. The existing data shows clear periodicity, but higher resolution observations will reveal finer structure. Is the pulse perfectly regular, or are there subtle variations? Do all the jets pulse in sync, or are there multiple active regions with different timing? How sharp are the transitions between active and inactive states? Answers to these questions will constrain the possible mechanisms. Second, they want to understand the composition. Is there anything unusual about what 3i Atlas is made of? Are there molecules or compounds present that we don't typically see in solar system comets? Are there signs of complex organic chemistry? The composition can tell us about the environment in which the object formed, and any significant differences from local comets would support the idea that interstellar objects can have fundamentally different properties. Third, they want to map the structure. What does the nucleus look like? Is it a single solid body, or is it more loosely bound? Are there obvious topographical features like craters, cliffs, or fractures? Is there evidence of layering or compositional variation on the surface? High-resolution imaging during the close approach might reveal details that have been invisible until now, and those details could be the key to explaining the pulsing jets. If there's a crater casting a shadow at just the right angle, or a fracture that opens and closes with rotation, that would provide the natural mechanism scientists are looking for. Fourth, they want to test predictions. Both the rotation hypothesis and the pulsing hypothesis make specific predictions about what should be observable. The rotation hypothesis predicts that the jets are continuously active and the brightness variations are purely due to changing viewing angles. If that's correct, then detailed observations should show a relatively steady stream of material, with the apparent intensity varying based on geometry. The pulsing hypothesis predicts that the jets actually turn on and off, so there should be phases where little or no fresh material is being expelled. Observations timed to coincide with the dim phases of the light curve should reveal which prediction is correct. Loeb has been vocal about his expectation that the December observations will provide clarity. In his writings, he suggested that by late December, we should have much more definitive data about the nature of this pulse. That's not just poetic language. It reflects genuine confidence that the quality and quantity of data expected from this observing campaign will be sufficient to resolve the question. Either the natural mechanisms will be identified and confirmed, or they won't. Either the observations will fit comfortably within existing models, or they'll demand new explanations. By late December, we should know which path we're on. It's worth noting that amateur astronomers are also part of this effort. While they don't have access to instruments as powerful as Webb or large professional observatories, they can contribute valuable observations. Distributed networks of amateur observers can monitor the object continuously, providing coverage that fills gaps in the professional observation schedules. They can document outbursts or sudden changes that might occur between scheduled observations, and they can participate in the collective effort to understand this visitor from another star system. There's something democratizing about that. This isn't just a mystery for elite scientists. It's a mystery for anyone with a telescope and the curiosity to point it at the right patch of sky. The December 19th date also creates a natural narrative deadline. It builds anticipation. It gives people a specific moment to focus on. And it means that the answers, whatever they turn out to be, are coming soon. We're not talking about years of analysis or decades of debate. We're talking about weeks. By the time the data is processed and initial analyses are published, we'll be moving into the new year with a much clearer picture of what 3i Atlas is and what the heartbeat pulse represents. But here's the thing about scientific investigations. Sometimes the answer you get is more questions. Sometimes resolving one mystery reveals another. It's entirely possible that the December observations will confirm the pulsing, identify some aspects of the mechanism, but leave other aspects unexplained. Science rarely delivers perfect, complete answers in one go. It's an iterative process. You gather data, you refine your understanding, you identify new questions, and you go back for more data. So while December 19th is a critical milestone, it might not be the end of the story. It might just be the end of the beginning. What's certain is that the close approach represents a unique opportunity. 3i Atlas won't come this close again. After it passes, it will continue on its trajectory, eventually leaving the solar system entirely. Future observations will become increasingly difficult as the object recedes and dims, so this is our chance. This is the moment when we can bring the full power of modern astronomy to bear on this mystery and see what it reveals. And whether the answer is mundane or extraordinary, it will add to our understanding of the universe and our place in it. That's what makes this exciting. That's why scientists are preparing so intensely, and that's why, even if you're not an astronomer, you should care about what happens next. Because this is one of those moments when science is genuinely exploring the unknown, and we get to watch it unfold in real time. Now let's talk about why this matters beyond just satisfying curiosity. It would be easy to dismiss the heartbeat pulse of 3i Atlas as an interesting curiosity, a minor footnote in the vast catalogue of astronomical observations. It's one comet exhibiting unusual behavior. So what? The universe is full of unusual things. Why should anyone who's not an astronomer care about whether jets are pulsing or just rotating into view? The answer is that this investigation touches on questions that extend far beyond the specifics of this one object. It's about how we approach the unknown. It's about what we're willing to consider when the evidence challenges our assumptions. And it's about what we might be missing if we're not paying attention. Let's start with the practical implications. Interstellar objects are messengers from other star systems. They carry information about environments we cannot directly observe. When we study them, we're learning about the diversity of planetary systems The processes that form and shape celestial bodies in different parts of the galaxy, and the conditions that exist in interstellar space. Every interstellar visitor is a data point, and when that data point exhibits unexpected properties, it's telling us that our models are incomplete. It's telling us there are phenomena we haven't accounted for. That's valuable information. If 3i Atlas has a natural mechanism producing the pulsing jets, and if we can identify and understand that mechanism, we'll have learned something new about comet physics. Maybe it will reveal a previously unrecognized way that internal structure can influence outgassing. Maybe it will demonstrate that comets formed in different stellar environments can have compositions or architectures that lead to behaviors we don't see in local comets. That knowledge feeds into our broader understanding of how planetary systems evolve, how organic materials are distributed through the galaxy, and what kinds of objects might deliver water and carbon-based compounds to planets. But there's also a deeper implication related to how we detect and interpret anomalies. We live in an era where our ability to observe the universe is advancing rapidly. New telescopes, new instruments, new analysis techniques are revealing details that were invisible just decades ago. As our observational capabilities improve, we're inevitably going to encounter more things that don't fit neatly into existing categories. More outliers, more anomalies. The question is how we respond to them. The easy response is to explain them away as quickly as possible, to find the nearest conventional explanation and move on. That's understandable. Scientists are busy people. There are grants to write, papers to publish, careers to build. Spending time on something that seems weird and doesn't have an obvious natural explanation is risky. It can make you look like you're chasing phantoms. It can damage your credibility if you turn out to be wrong. So there's institutional pressure to stick with safe interpretations, to avoid speculation, to focus on what can be easily explained within established frameworks. But that approach has a cost. It means that truly anomalous signals, things that genuinely don't fit our models, can be overlooked or dismissed. It means we might miss opportunities to discover something fundamentally new because we're too focused on fitting everything into existing boxes. Loeb's willingness to ask uncomfortable questions about Oumuamua and now about 3i Atlas is a counterbalance to that pressure. He's saying that when something doesn't fit, we should investigate it seriously, not brush it aside. We should be willing to consider explanations that challenge our assumptions, even if those explanations seem unlikely. This has direct relevance to the search for extraterrestrial intelligence. One of the long-standing criticisms of SETI is that it focuses almost exclusively on radio signals, looking for deliberate transmissions from other civilizations. But what if other civilizations don't communicate via radio? What if they use methods we haven't thought of? And what if, instead of sending signals, they send physical objects? Probes, artifacts, messengers. If such objects pass through our solar system, and if we're not looking for them or not willing to consider that possibility when we encounter something unusual, we'll miss them. The heartbeat pulse of 3i Atlas is exactly the kind of signal that could be overlooked if we're not careful. It's subtle. It requires detailed analysis to detect. It doesn't announce itself as obviously artificial. If scientists hadn't been paying close attention to the light curve, if Loeb hadn't taken the time to run the calculations and question the standard interpretation, this pattern might have been noted briefly and then forgotten. The object would have been catalogued as just another active comet. The opportunity to investigate further would have been lost. So the investigation of 3i Atlas is, in a sense, a test case. It's testing whether we're capable of recognizing and seriously studying anomalies that don't fit our expectations. It's testing whether our scientific institutions are flexible enough to accommodate unconventional questions. And it's testing whether we can balance healthy skepticism with open-minded curiosity. Those are important tests because as our technology improves and we observe the universe in greater detail, we're going to face more of these situations. We need to develop the habits and frameworks that allow us to handle them well. There's also a philosophical dimension to this. Human beings have always wondered whether we're alone in the universe. It's one of the oldest questions we've asked. For most of history, we couldn't do much more than speculate. But now, for the first time, we have the tools to actually investigate that question scientifically. We can search for biosignatures on exoplanets. We can monitor radio frequencies for artificial signals. We can study objects that enter our solar system from interstellar space. And each of those approaches brings us closer to an answer. The discovery that we're not alone, if it happens, won't necessarily come in the form of a dramatic announcement or an unambiguous signal. It might come gradually, through the accumulation of evidence. A molecule detected in an exoplanet's atmosphere that suggests biological processes. A radio signal with patterns that can't be explained naturally. An object exhibiting behavior that doesn't fit with known physics. Any one of these, by itself, might not be conclusive, but together they could build a case. And the heartbeat pulse of 3i Atlas could be part of that case, or it could be a lesson in how to properly investigate such signals when we encounter them. Even if 3i Atlas turns out to be entirely natural, even if every anomaly has a conventional explanation, the process of investigating it has value. It demonstrates that we're willing to ask hard questions. It shows that we're not content to simply catalogue observations and move on. It proves that when something doesn't fit, we're curious enough to dig deeper. That attitude, that willingness to investigate the strange and the unexplained, is what drives scientific progress. It's what leads to breakthroughs, and it's what ensures that when we do encounter something genuinely new, we'll recognize it. The broader public also has a role to play in this. Science doesn't happen in a vacuum. It's funded by societies, conducted by institutions, and communicated to people who may not be experts but who care about what we're learning. When the public is engaged, when people are curious and asking questions, it creates an environment where scientists feel supported in pursuing unconventional research. It creates demand for answers. It makes it harder for anomalies to be quietly dismissed or ignored. That's part of why communicating about objects like 3i Atlas matters. It's not just about educating people on the latest astronomical news. It's about inviting them into the process of discovery. It's about sharing the uncertainty, the questions, the excitement of not knowing what we're going to find. And it's about building a culture that values exploration and curiosity, even when the answers aren't immediately obvious or comfortable. So when you ask why the heartbeat pulse of 3i Atlas matters, the answer isn't just about this one comet. It's about how we approach mysteries. It's about what we're willing to consider. It's about building systems and habits that allow us to recognize genuinely anomalous signals when they appear. It's about keeping open the possibility that the universe still has surprises for us, and that some of those surprises might challenge everything we thought we knew. That's why this matters. That's why it's worth paying attention. And that's why the December observations are so significant, because they represent a chance to move from questions to answers, from speculation to knowledge. Let's bring this all together and talk about where we go from here. So here we are. We've walked through the evidence. We've examined the observations showing that 3i Atlas pulses like a heartbeat, brightening and dimming with precise regularity every 16 hours. We've explored R.V. Loeb's mathematical analysis, demonstrating that this pattern is more consistent with jets that actually turn on and off, rather than just rotating in and out of view. We've considered the implications, from natural mechanisms involving unusual internal structures to more exotic possibilities that challenge our assumptions about what interstellar objects can be. We've looked at the broader context of other anomalies and how they fit into the puzzle. And we've discussed what's coming next, with the critical December 19th close approach that promises to deliver much more detailed data. Now comes the question that matters most. What do you think is happening? Because this isn't one of those situations where scientists have all the answers and the rest of us just wait to be told what to believe. This is an active mystery. The data is publicly available. The analyses are being published and debated. The observations are ongoing. And the answer isn't settled. So you, as someone who's now informed about the evidence, get to weigh in. You get to consider the possibilities and form your own opinion. Are we looking at a comet with an unusual but natural structure that happens to produce pulsing jets through some clever arrangement of internal reservoirs, vents, and rotational dynamics? That's entirely possible. Nature is creative. It produces phenomena we don't expect all the time. And just because something is rare doesn't mean it's impossible. Maybe 3i Atlas formed in an environment that gave it properties we don't see in comets from our own solar system. Maybe its composition or its history included collisions or near misses that fractured its interior in just the right way to create the mechanism we're observing. If that's the case, then the December observations will reveal those features, and we'll have learned something fascinating about the diversity of objects in the galaxy. Or are we looking at something that doesn't fit neatly into the category of natural comet? Something that exhibits a level of regularity and control that suggests an internal mechanism we don't fully understand? That doesn't necessarily mean it's artificial. It might mean there are natural processes we haven't accounted for. It might mean that our models of how comets behave need to be expanded, but it also opens the door to considering whether some interstellar objects might be something other than random chunks of rock and ice drifting through space, whether they might carry information, or even intent, from elsewhere in the galaxy. I'm not here to tell you which answer is correct, because I don't know. Nobody knows yet. That's the honest truth. The data we have so far is intriguing but not conclusive. The December observations will help, but even they might not provide a definitive answer. Science often moves slowly, piecing together evidence over time. But that's also what makes this exciting. We're witnessing a real scientific investigation as it unfolds. We're seeing the process by which mysteries get examined, hypotheses get tested, and understanding gets built. And we're doing it together. What I do know is that questions like this matter. They matter because they push us to think beyond what's familiar. They matter because they remind us that the universe is vast and strange and full of things we haven't figured out yet. They matter because the process of asking them, even when the answers are uncertain, is how we grow our knowledge and expand our perspective. And they matter because every now and then, a question like this leads to a discovery that changes everything. If you've made it this far, if you've stayed with me through this entire investigation, then you're the kind of person who values curiosity over comfort. You're someone who's willing to sit with uncertainty and complexity rather than demanding simple answers. You're someone who understands that the most interesting questions are often the ones that don't have easy resolutions. And that means you're exactly the kind of person who should be part of this conversation. So here's what I want you to do. First, hit that subscribe button if you haven't already, because when the December 19th observations start coming in, I'm going to be covering them. We're going to look at the new images, the spectroscopy data, the high-resolution analysis of those jets. We're going to see what the telescopes reveal and what it means for the heartbeat mystery. You're not going to want to miss that. This story is just getting started, and the most important chapter is about to be written. Second, drop a comment and let me know what you think. Do you believe there's a natural explanation for the pulsing? And if so, what do you think it is? Or do you think we're looking at something that challenges our current understanding? Are you more convinced by the rotation hypothesis or the pulsing hypothesis? And what would it mean to you if the December observations reveal something genuinely unexpected? I want to hear your perspective, because these kinds of mysteries are more interesting when we're exploring them together. Third, if this video made you think, if it gave you a new perspective on what's possible or challenged some assumptions you had about how we study the universe, then hit that like button. It tells me that this kind of deep dive content is valuable, that people want more than just surface level coverage of space news. And it helps other people who are curious about these questions find this video and join the conversation. The reality is that we're living in an extraordinary time for space exploration and astronomy. We have telescopes that can peer back to the earliest moments of the universe. We have rovers exploring the surface of Mars. We have probes visiting asteroids and comets in our own solar system. And now, we're detecting and studying objects from other star systems as they pass through our neighborhood. Each of those objects is a window into the wider galaxy, a chance to see what exists beyond the boundaries of our own solar system. And sometimes, those objects surprise us. 3I Atlas is a surprise. The heartbeat pulse is a surprise. Whether it ends up having a conventional explanation or not, it's a reminder that we don't have everything figured out. There are still mysteries out there. There are still phenomena that don't fit our models. And there are still opportunities for discovery that could reshape how we understand the cosmos and our place in it. The December 19th close approach is just weeks away. By the time the data is analyzed and the results start to come in, we'll be moving into a new year with potentially new answers or new questions. Either way, it's going to be fascinating, and I want you to be here for it. I want you to be part of the community that follows these investigations, that asks the hard questions, that doesn't settle for easy answers when the evidence demands deeper thinking. Because at the end of the day, this isn't just about one comet with a pulse. It's about how we approach the unknown. It's about whether we're brave enough to look at data that doesn't fit and ask what it means rather than dismissing it as noise. It's about maintaining the wonder and curiosity that drives science forward. And it's about recognizing that sometimes the universe has something to teach us if we're willing to listen. So stay curious, stay engaged, and keep watching the sky, because 3i Atlas is out there right now, pulsing like a heartbeat, carrying secrets from another star system. And in just a few weeks, we might finally understand what that heartbeat means. I'll be here to walk through it with you when the time comes. Until then, keep asking questions, keep thinking critically, and keep looking up. There's always something new to discover,